Okay, let's get rid of that. Let's go here.
Right, hi everybody. We now introduce Rich Wurzbach, president of MRG Laboratories. He will be giving insights on establishing on-site grease analysis capabilities with mini lab screening tools. Right, on to you, Mr. Wards. Rich.
Great. Thanks, Eddie. I'll share my screen here for everybody and go right into my presentation. And Eddie, that looks good for us. We good to go?
Yep, yep.
All right. Thank you very much. So I'm going to talk about establishing grease analysis capabilities on site with some screening tools. And I'll start today with a little bit of background on sampling. I'll talk about the instruments that have been developed and are being developed and how they can be used effectively to do some of the analysis of grease that maybe historically has not been part of analysis for a lot of folks. So the first question might be why do we sample and analyze greases? You know, we it's well understood of the value of oil analysis, and I've been listening to some of the presentations so far today, and many of them have touched on that, analyzing gearbox oils, hydraulic fluids, turbine oils, and so forth. But greases haven't quite gotten the time, quite the attention that we have on the oil side of thing. But in many cases, they're no less important. For why might we analyze greases? Well, for in-service greases, the warning signs are often evident in the grease prior to failure. And if we can find these early signs, then actions can be taken to mitigate that damage. You can see in the picture that I've added here, this evidence happens to be on the outside of the machine where there's our Zerk fitting for adding grease. And you can see some kind of orange brown grease, but also some dark green grease. And right off the bat, you're thinking there's something wrong here. Two different products are being added to this machine. It can cause some issues. But wouldn't it be great if we could evaluate what that impact is by being able to sample and test that grease? By doing so, we can identify systemic issues by getting to the root cause of lubrication problems. We can look for contamination or compromised lubrication and trace that back to its source. And then we can look at wear levels and compare that in similar equipment. We can trend that with routine sampling and create criteria that helps us with decision making about lubricated equipment. The value of on-site grease analysis is that samples can be quickly screened against some criteria for kind of a pass-fail designation. Are things going okay here, or do we need to dig deeper and find out just exactly what's going on? Samples that don't pass can be sent out to a laboratory for further analysis. And when we get that feedback from grease analysis, we can use that to optimize lubricant use. So I'm going to talk about two core tests that can be done for grease that are very quick, very simple to perform, even in the field or right at the machine, which cover a wide range of parameters that can change on both the machine side, where it's looking at the wear of the machine, but also looking at the condition of the grease through its appearance and color. Samples can be taken during scheduled maintenance, or some cases while the equipment's running, and that immediate decision and action can be vital for some applications. Uh, when we get we identify some key parameters and quickly test them. It usually is done while we retain a majority of the sample for future testing if needed. So if we screen through, let's say we take 50 samples from different machines, we screen through and find 5 of those 50 exceed some criteria. The others can be set aside, disposed of, what have you. They all, things look good. Those machines are fine. But the 5 that were outliers, we're really not consuming much, if any, of the sample in this screening process. And therefore, we can retain those 5 samples. We can make a decision about doing further analysis, maybe right there with some other instruments at the site, or even packaging it up and shipping those samples to a laboratory that can do additional in-depth analysis. So we're going to talk about the on-site ferrous detection and color detection, or changes in the appearance of the grease, and about how we use them to test the grease conditions and be able to pick up bearing or gear wear in under 5 minutes. So it's a very quick test. It's really closer to a minute or 2 at the most, once we get good at things, understand how to use it, and just go right on down the line using these instruments. Offsite, we can use lab ferrous debris, colorimetry, FTIR. These same instruments that I'm going to share with you can be used in a lab and then test very economically, including the cost of the sampling tools that are really integrated into this process, especially if we apply some automation. So once we start to gather this data, we can group things together. And here you can see some wear concentrations that were done for a large number of wind farms for one particular wind farm operator at multiple sites. And there was such a variation in the wear concentration that we had to use a logarithmic scale in this case to kind of put all the data together on the same chart. And we were able to apply criteria, kind of a green, yellow, red designation for them. But you can see some groupings here, and there is obviously one group of machines, or wind turbines in this case, that are consistently high when it comes to ferrous wear. When we see that grouping, we start to ask questions. Why is that? And why is it different than the rest of my fleet? And in this case, it was found that there was a completely different maintenance strategy being employed here. Grease was being added much less frequency, wear was accumulating, and that particulate was becoming a problem. So you can look at the data in a very kind of raw way, present it graphically like this, and really get some good insight. But the first thing we have to do is realize that when we're analyzing grease, it's different. It's not the same as oil analysis, and that's because grease is not oil. It behaves differently. We usually think, about properties of oil. First thing we talk about is viscosity. Viscosity is the property of oil that sets that lubricating film. It dictates how oil flows, and it is the primary parameter that prevents wear. The main reason we're using lubricants in the first place, prevent wear. Grease, however, is an oil, but it also has this thickener. We describe the behavior of grease as non-Newtonian. It doesn't behave in the same way. Its viscosity, or its viscous behavior, is different than oil would be. And it is designed to stay put in the machine. So oil is, with the help of gravity, is looking for a way out of the machine. And if we have a valve, we can open that valve and gravity does the work for us. It helps us get the oil out of the machine into a container, a sampling container where we can analyze it. But grease is fighting us. Grease wants to stay in the machine. It wants to adhere to the surfaces to which it was applied. And therefore, the same tools that are effective for oil analysis will not be effective for sampling, or for oil sampling, will not be effective for sampling grease. So dynamically, and we may get this impression that grease is just a lump. It's just this pile of material that stays in one place all the time, because when we would pick some up or we open up a machine, that's what it looks like. The truth of the matter is that dynamically, under machine operating conditions, when things are moving, when gears are moving, when bearings are rotating, grease does flow. It does flow, but only very close to that bearing, to that gear, to those moving parts. And so it's important to recognize that there is a target zone in grease lubricated equipment that must be accessed effectively so that we can extract that grease, we can pull it out of the machine. And so that's much different than oil. So the sampling and analysis techniques for oil, we find, are inadequate for grease. So over time, this has been addressed and continues to evolve through the development of samplers. And there are samplers available that have been available for more than 10 years now that aid in this process. There are designs that maintain a purge function for grease with little or no back pressure for drain applications. So if our opportunity to access grease in a machine is to capture it while it's coming out of the machine through a drain, we can, in some cases, put this sampler, this grease thief, right into that drain and allow it to capture the grease on its way out. If there is more grease coming out than the volume of this sampler, then it will allow relief. There's a relief path for it. So this, just for reference, the grease thief, the sampler that you see on the left side, that's almost, let me just check. Yeah, it's almost the exact size on my screen anyway. And it is just a few centimeters long, and it holds 1 gram of grease, a little more than a gram of grease. That's the target volume. And so we want to catch 1 gram of grease on its way out of the machine before it touches the outside of the machine, before it lands on the ground, before it mixes with other materials that are not representative of what's in the machine. And if you look at this red piston that you see there, if you look at the diagram at the bottom, just to the left of the piston, you see a little circle there, and that's an exit hole. That's a relief hole. So we can thread this into the machine, fills up, the excess grease comes out, and now we have a representative sample of the most recent grease to leave the machine. Other times, we need to go in and get that grease. It's not coming out. It's in an enclosure, a housing, and you can see to the right the tool that is used. It's an adjustable tool. It holds that sampler, that thief, so that it can be inserted into the machine to a known depth. Then it can core the sample and extract it. A lot of folks think that, well, suction works really well for oil, so I just need a stronger suction and I can pull out the grease. And that's not necessarily true. It can work for extremely soft and runny greases, of which there are some, but the majority of the time that is not going to be effective. So we have these tools that can core the grease. So it's really become a standard. There's been publications by the Electric Power Research Institute. The wind energy industry in Denmark did some studies, some research projects to develop and designate it as an effective sampling tool. ASTM D7718 is the standard for sampling greases from in-service equipment that outlines the use of these tools. ASTM D7918 is now the standard method for in-service grease analysis for up to 6 tests, including the 2 that I'm going to talk about. And organizations like the American Wind Energy Association, now known as Clean Power, published recommended practices for grease sampling and analysis. So you can see the different kits here that are available, different applications, pillar blocks or pillar blocks, as we might call them, electric motors, gearboxes, robots, grease lubricated robots, wind turbines, and then even a device that lets us take samples from very small openings down to about 7 millimeters in diameter. So we get in there to get that machine. The kits with the barcodes and the smartphone app can collect the sample data in the field so that all that information is retained. These all conform to the ASTM standard, and then that sampler, that small thief, becomes the analysis tool. It has that clear plastic body. We can do colorimetry, as we'll show, and some direct ferrous measurement. So the direct ferrous measurement is the first thing. Fortunately, most grease lubricated components are ferrous metallurgy. There are some exceptions. There may be occasionally a brass cage, and there might be some non-ferrous bearings, but we can tell a lot by looking at the ferrous content using an inductive coil. It measures that ferrous content, and you can see the handle of that grease thief sticking up the top of this. It's capable of measuring samples up to 200,000 parts per million. I'm going to talk a little bit about spatial distribution errors, because grease is generally heterogeneous when we go to analyze it. What do we do with an oil sample? We shake that bottle up really good. We evenly distribute the particulate and any contaminants, and then we do the analysis. But you can't do that with grease. You can't shake up grease. And so we're always going to end up with an uneven distribution of particulate, even when it's wear particles like this. So we have to measure that heterogeneous distribution reliably. And so we've done some studies with different types of instruments. Here, this is an obsolete instrument that was being used for some time, called the FDM on the left, and then this FerroQ device that you see on the right. We did some side-by-side comparison. We prepared some of these samplers using a resin and miniature ball bearings. You can't even see them in this clear resin. They're so small. But we did that to allow that ball bearing to be at different heights so that we could measure the response. We generated what was essentially an equivalent of 1,000 ppm of ferrous material by putting that in, and then put it near the bottom, in the center, at the back end, and just to see how these instruments would respond. And you can see a plot of that. This is a comparison of this older FDM unit, which is the blue graph, and the orange graph is this FerroQ device. The measuring principle is similar, and then they're both looking at the induction, but in the way in which the coil measures is quite different. The FerroQ actually tracks the sample as it's being inserted and measures the total amount of material that passes through that entire coil measuring zone, whereas the FDM and most other ferrous measuring devices like PQ are using a static measurement. So what you see here is that very clearly, with about 1,000 parts per million basically spiked into this sample, across from one end to the other, you can see that it's a very stable. You only get a bit of a drop off from this FerroQ device near the very end. Okay, so right behind the piston, if there is a concentration of ferrous debris there, you'll have a little bit of signal drop off. But when you look at the other device, it's over reporting when it's down near the bottom, and what's up at the end, it might be showing almost no ferrous content. So basically, you could have large chunks of wear in that sample and it's not reporting them. So it is very important that we use an instrument that's able to differentiate that. So I wanted to share that. It's a quick test. It just takes a few seconds, and we have a reliable concentration of the ferrous content. The other key parameter that we want to look at here is color. And so we've developed this grease colorimeter. It can detect darkening in color due to grease aging and oxidation. It can look for evidence of mixing and other changes. And the path length, what we found is that the path length of the grease film that you expose for measuring the optical response or the color response is very critical to color. And you can try this on your own. You can take a lump of grease and put it on a piece of white paper, and then slowly drag that across the paper until it gets thinner and thinner. And you'll see the color change based off of the thickness that is presented to that white background. Same thing when we try to measure with a spectrometer. So we've been able to identify the accumulation of particulate, other contaminants, because we can adjust and vary the thickness of the grease. A little dab is put onto the window of the spectrometer, and then the handle is lowered to squeeze the grease down to a known film. This works with 3 different settings. We have spacers in there, so you can measure it at it's about a millimeter of thickness as an initial test, which we define as 0.035 inches, and then at 10 thousandths of an inch, 10 thousandths of an inch, and 5 thousandths of an inch. So really down to a fraction of a millimeter at these set thicknesses. And then the comparison is made to the reference grease. So here on the right, you can see the output of the spectrometer. On the left side of each of these representations is the baseline grease. It's that light tan grease. When you look to the right half of each of these, you see what the in-service grease is. And you can see there was a minor change in the first case, a very slight change, and we are measuring using the CIE values. You've got that delta E value. On the right, you have severe oxidation in the grease, and it's obviously undergoing quite a different change there. We have a delta E of 44. So over time, you'll develop criteria that says these greases are all fine. They get a little bit darker in service, but when they exceed a certain value. And so, for instance, for robots that are a great palette as far as that goes, because it's typically a very light tan grease like you see here, we've established a criteria of delta E of 15. And those of you who have worked with the CIE values in MPC testing, know what that delta E value is. We can apply it here as well. But you can't just aim a spectrometer at a clump of grease and get meaningful data. The path length is critical. That's why this colorimeter carefully squeezes down the path length to a precise value that can be repeatedly measured and then compared to the baseline color. So what can we do with this data? Here's some results. This is from a wind farm, and we have 20 some different wind turbines here looking at main bearings, and this is the ferrous screening results. Again, how to create kind of a logarithmic scale to get them all on the page, but you can see a green line and a red line, and the majority of these samples look good. They're in the hundreds of ppm, maybe a little over 1,000, getting up towards 2,000. But the real outliers here, first we have a yellow that's a caution at about 8,000, 10,000 ppm, and then 2 real outliers, turbines 47 and 52, that are over 60,000 ppm, over 100,000 ppm actually, that require attention. But not to ignore number 53, because when we have the crane out to do those repairs, it could be important to also, at the very least, inspect that to see if from an efficiency standpoint, we should be looking at that as well. And then here's some of the color data, the delta E color data, which is looking at something a little bit different. Yes, sometimes the wear particles are the reason for a color change, but you can have very low ferrous levels and have significant color change, and it could be due to someone used the wrong grease. Someone did not change the grease often enough, so the grease is now oxidized and degraded. And so color is kind of this kind of catch-all. You don't know what changed, but the color changed enough that you could then do that follow-up analysis. So the grease screening applications that we've seen include using for robotics. I mentioned that in the presentation. These are typically 6-axis robots. Robots are made across Europe and a lot in Japan and then some other countries now. But the Asian build robots tend to be the ones that are grease lubricated. Some of the European robots are oil lubricated. So we focus on the ones that are grease lubricated. And there's a kit and you extract it. And this is a really great screening process. Again, because of the light starting color of the grease, you can see that. And really, what prompted me to develop a colorimetric method for greases was working with a robot automation technician, a repair technician, who we were out in the field taking samples one day. We took a bunch of samples from a number of different robots. And, he said to me, robot 3 and robot 8 are going to be your problems. I'm like, oh, do you have other data that you know that? He says, no, I can just tell by looking at the grease. So what do you see? He says, I don't know. They just look different. So it's a validation that there is a color change, that there is an appearance change that can be measured. And as long as we do a good job sampling and a good methodology for consistent color comparison, we can generate criteria that can screen through large amounts of samples. I talked about wind turbines. Nuclear power plants are another application. We can take these small devices right into the plant. They're battery operated, Bluetooth, and we can take them right where decisions need to be made, sometimes in a very timely manner. Other times it's maybe a high radiation area. It'd be very difficult to get the sample out of the plant. Railway is another great application. We're testing a lot of wheel bearings. We've tested traction motors and using sampling tools, the grease thief sampling tool that can extract that. We can screen through a large number of samples, and we're doing this now. We're doing thousands of samples per month. And screening through them to look for these wear conditions. And when it exceeds our criteria, then we can take those on and do more detailed analysis to find out what is the nature of that. And again, it's a very quick turnaround type of process, because once that locomotive comes in for maintenance, you don't have a lot of time to sit for samples to be sent off and to make their way back again days later. It's too late then. The locomotive already has a bunch of cars attached to it, and it's out on the track somewhere. We need that quick turnaround, and this on-site, at-machine screening tools can do that for us. There's marine applications. I just got finished being an expert witness on a loading crane on a ship that collapsed because the grease was not being monitored. There was a bearing issue. Resulted in an injury, and that's how it ended up in a court case. So you can imagine the impact of that wear and what we could find very early in the process by sampling and analyzing greases from these slewing bearings. Mining, food production, preventing bearing wear. You hear these reports about a recall for small metal particles in chicken or something like that. Guess where they came from? The small metal particles are coming. If they were large metal particles, they'd be caught by the magnetic detectors. The small metal particles are bearing wear, and we can find that early with these kind of tests. So this is the things I wanted to share with you today. Even grease manufacturing, we can check cleanliness. We can set a color target and make sure that the quality of the grease is there. So the conclusions, these are proven tools and standards. They're available for representative sampling. We can complement condition monitoring, especially in slow speed shafts where other technologies fail to pick things up. We can save time and allow immediate decision making. We can optimize grease usage, which increases sustainability by reducing consumption. And it really can be quite a low cost screening process. We can attach things later like FTIR, use a vapor probe for moisture, and kind of build a mini lab. So my message to you is don't overlook lubricant health and machine health data when machines are grease lubricated, because we have the tools, the data is there, and you can set up to do this kind of analysis in your facility or your laboratory. So thank you, and I'll see if we have any questions.
Hi, yep. Hi, thank you, Rich, for the presentation. Very in-depth. If there's any questions, please feel free to type in the chat box.
Yeah, great. While we're just seeing if anybody comes in late on this, yeah, the applications continue to grow. I know that the folks from Ecol have made a couple presentations already this morning, and it's great to see that. And that's another laboratory that's using these kind of technologies, using the ferrous debris scanning and the colorimetry and so forth, and really seeing how they can integrate that in a kind of an end-to-end solution for wind turbines for them is a great application. So I really believe that I know there was some talk earlier. I think Pierre Vanderkellen was talking about some of the statistics out there on the long-term use of lubricants, and that it's actually going to grow as we go into the future. I believe on the grease side of things, we're wasting most of the grease that we're using. And it's just a human nature thing. Just add more grease till it comes out somewhere. But if we start to test it, we can get towards optimization. And we did a project for the military, for the Chinook helicopter fleet, that resulted in reducing greasing tasks almost in half, with an estimated savings for that fleet of close to $100 million per year. That's what we're talking about. Reducing time, increasing safety, time in the field, and reducing the consumption of this resource, which is a very sustainable approach.
Yes, well, thank you for the conclusion, Rich. We're saving money. That's what we're all about.
Yes, it is. Well, thank you for your help here. Appreciate everybody that sat in, and look forward to seeing y'all at some of the other sessions coming up. Thanks.
All right. Thank you, Rich. Thank you. Bye. Bye, guys.